Hello everyone and welcome back to Nunley Math. I'm Aaron Nunley. Thank you so much for joining me here today for the fourth video in our series of videos on the linear function or linear equations. In our first video, we discussed the standard form of a linear equation, and in the two videos that followed that, we spent some time talking about the slope-intercept form of a linear equation. Today, I have a third form of a linear equation that I wanted to show you that I actually find to be very, very helpful and extremely fascinating, actually. Notice this is called the point-slope form of a linear equation, the point-slope form of a linear equation. And the reason I like it so much is because of how we develop this particular pattern or formula. Notice that we start off here with the slope formula that we talked about in previous lessons. You'll notice that the slope of our line is identified by the letter m, and we say that the slope of our line is the ratio that compares the rise of our function or our graph to the run of our function or graph. Or in other words, how much do your y values change when compared to how much your x values change? Now, the purpose of this lesson is not to review the idea of slope. We do have some other videos on that, so if this formula is unfamiliar to you, or if you are uncomfortable with this formula in any way, you really need to go back and make sure you understand that first. Because what I'm going to do today is I'm actually going to take this slope formula and I'm going to rearrange it to create the point-slope form of a linear equation. So part of the thing that I think is very confusing in math is a lot of times we'll give you formulas or forms or patterns but never discuss where they come from. So it's important to me to make sure that you realize that when we talk about the point-slope equation, all we're going to do is take a formula we've already discussed and use the properties of algebra to rearrange it a little bit into a form that's more useful or helpful for us. So I'm going to do that. I do think it's important to mention that this is often confusing for students and can often be a little overwhelming when you see it the first time. So I'm going to recommend that if you find it to be a little challenging, you go back and watch it a couple times and that maybe you pause along the way to think about what we do at each step. I also tell the students in my class that it is not an expectation for me in Algebra 1 that you as a student would recreate this process on a test. It would make a great extra credit problem on a test, but I would probably not ask my students to do what I'm about to do. Instead, the important part or the priority is that you see it worked out and that you realize that the formula or pattern I'm giving you does indeed come from somewhere. It's not something that your math teacher just made up out of nowhere. So having said all of that, I know that's a really long preface. Here's what I'm going to do. I'm going to try and rearrange this in a very particular way. Notice that my slope is equal to the difference in my y's divided by the difference in my x's. I'm going to try and rearrange this just a little bit so that my y's are by themselves. I want to get the y's on one side of my equal sign, and I want to get everything else on the other side. So to do that, I'm going to have to move this x2 minus x1. Now, notice I did go ahead and put in some parentheses. The reason I did that is because this long division bar already acts like a grouping symbol, but some students don't necessarily see that or think about that unless I put the parentheses in. So I have this quantity divided by this quantity. We learned in previous lessons that we can rearrange equations by using different properties. Specifically today, I'm going to use the property of equality first. The property of equality says I can do anything to an equation I like as long as I do the same thing on both sides. Or whatever I do to one side of my equation, I also have to do to the other. So I'm going to look at this and say, you know what? These y's, or this quantity, has been divided by these x's, or this quantity. If I would like to get rid of that division, I need to use the inverse operation, which is multiplication. And I'm going to multiply both sides by this x2 minus x1. Now, because this is a long division bar and it has the y's have been divided by this entire thing, no matter what these individual x's are, eventually they're going to make a single number. This might be a 9 minus 5, so it might be divided by 4. This could be a 10 minus 7, it could be divided by 3. It doesn't really matter what this number is inside these parentheses. If I divided by it, to get rid of it, I have to multiply it by the same thing. So it's probably less confusing for you if I write this as x2 minus x1 over 1, because then you can see that all we have to do is our multiplying fractions rules, which say that we can cross simplify these values, and they simplify to a 1. And then I just multiply this together. y2 minus y1, that whole thing times 1 is going to stay the same, and 1 times 1 is going to be a 1. This is going to simplify on this side to just the y2 minus y1. Notice over here on the left, I have x2 minus x1 times the m. That brings me to this step. I've got the y's by itself. I'm still going to rearrange this just a little bit more. Notice over here on the left, you have a value multiplied by m. The commutative property of multiplication says if this is multiplication, it does not matter what number I put first. So instead of having my x's first and my m second, I put my m first and my x's second. If you were in my class, I would actually write out commutative property for you here off to the side. I did not include that in this slideshow because it got a little bit crowded. There's a lot that happened on this slideshow. If this makes sense so far, I'm going to go ahead and do something else here. I'm going to use the symmetric property, or the property of symmetry. That says if you have a quantity that's equal to another quantity, it doesn't matter which side of the equal sign you put those values on. If this equals this, I can switch what side, and I can say the y's are equal to what we had on the other side. Remember, it does not matter. If this equals this, I can put them on different sides of the equal sign, and I end up having the exact same thing. Still okay? That's a lot, isn't it? One more thing I want to do, notice that in my slope formula, I had 2 known y's and 2 known x's. In our last lesson, we talked about how when you have 2 coordinates, you can use those to solve and find the slope. I'm going to use this equation for a different purpose. Instead of having 2 known x's and 2 known y's, I'm actually going to change this so those x's and y's are unknown. Take a look here. This is no longer a y and an x that I know. It's now a y and an x that is unknown. I can do that. I can switch known values to unknown values in order to show the relationship in a more general way. So when you're finished, what you end up with is y minus y1 equals m times x minus x1. Notice I got rid of the parentheses here because there really is only one operation. It's just the subtraction. So the parentheses are unnecessary. The job of the parentheses is to tell me what to do first. Since there's only subtraction, I don't need them. This last step right here is the point slope formula. You can see how we take the slope formula, and if you just rearrange it just a little bit, you can actually create this. You still have your slope, you still have the difference in the x's, you still have the difference in the y's. It's just rearranged in a different way because we're going to use it for a different purpose. And here's what that purpose is. Notice what the directions here say. It says use that point slope equation to find the equation of a line when you know the slope has a slope of 3 that passes through the point 5, 2. Think about how this question is different from the questions we did in the previous lesson. In the previous lesson, we would have a slope, and they would give us the y-intercept, and then we would create our equation in slope-intercept form. What's nice about the point slope formula is I can use this to find the equation of a line regardless of what point they give me. This no longer has to be the y-intercept. All I have to do is come through here and plug in the values that they give me in for my slope and for my known x and y. Take a look. If my slope is 3 and my only given x is 5 and my given y is 2, and I plug those in, I get y minus 2 equals 3 times x minus 5. I just took the 3, the 5, and the 2 and plugged them in where they belonged. I now have the equation of this line. And then I'm going to take this equation and I'm going to simplify it just a little bit using the distributive property. I'm going to pass the 3 out, and I get y minus 2 equals 3x minus 15. And then I'm actually going to go ahead and get rid of this minus 2 by adding 2 to both sides. And when I do that, what I'm left with is y equals 3x minus 13. Notice, I was able to take my slope and a given point and then find the equation of the line and then convert that line into slope-intercept form. The point-slope equation gives us a quick and easy way to get the slope-intercept equation even though I have not been given the y-intercept. Does that make sense? Let's try another one. Use the point-slope equation to find the equation of a line with a slope of negative 2/3 that passes through the point 1, 4. Again, they have given me the slope, and they have given me a point that is not the y-intercept. I always have my students rewrite the original pattern. Remember, writing the pattern does 3 things for us. Number 1, it helps us keep our work organized. Number 2, it helps whoever is reading our work to understand what we're doing. And number 3 is it does help us to memorize that formula. In the case of this problem, my slope is negative 2/3. That's given. The only x that I know is the 1. The only y that I know is the 4. I'm going to plug these values into this equation. Then I'm going to simplify it to slope-intercept form. Distributive property to pass out that negative 2/3. Notice I have a negative negative here. That's kind of messy. I'm then going to add my 4 to both sides. Notice when I add those together, my minus negative 2/3 would become a plus positive 2/3 plus positive 2/3. That's 4 plus 2/3, which is 4 and 2/3. Notice my equation slope-intercept form, I have a slope of negative 2/3. I have a y-intercept of 4 and 2/3. So if I were to graph that, I would start off up here just above the 4 and below the 5 on my graph. It'd be right about there. And I would go down 2 over 3, down 2 over 3. And you get a graph that looks something like that. But we've already practiced graphing those. Let me clear this off. I'll tell you what, take just a second, try this next one on your own. I'm going to recommend that you pause the video to do that. And then if you feel pretty confident in your answer, you can skip through my explanation, skip right to the end and see if they match. I'm going to go ahead and work through this. I start with my pattern. Remember, we always write that down first. I know my slope is 7. I know my only given x is 3. My only given y is 5. And I plug those in. I'm going to take that 7 and distribute it to everything in the parentheses. Then I'm going to add 5 to both sides, and you end up here. How's that look? Hopefully you're getting pretty good at that at this point, because I am going to take what we've done here and I'm going to stretch you just a little bit farther and see if we can solve some more challenging problems. Suppose you're asked to write an equation for a line that passes through the point 1, 3 and the point negative 2, negative 3. Remember, in order for us to use the point-slope formula, what we're going to have to do is we're going to have to have a point, and we're going to have a slope. Well, in this case, notice that I have a point, and I have another point, but I don't have a slope. It's a shame there's not a way that we could find the slope when we have 2 points. And obviously there is a way to do that. Hopefully you recall that we have a slope formula. Remember, in order to use the point-slope form, I need to have a slope, and I have a way of calculating that slope. So I'm going to take these numbers, and I'm going to plug them into my slope formula. Let me erase all that. I'm going to plug those into my slope formula. Remember, it does not matter which of these is x1 and y1, which one's x2 and y2. What is important is that the x2 and y2 are together. When I look at how I did this on my slideshow, I made this x2, which means this had to be y2. That made this x1, and that made this y1. That's a terrible drawing one. There you go, y1. And when we do that, we plug those in, we come up with a slope of 2. Now, keep in mind, if I had made these x1, y1 and had made this x2, y2, I would have got the same result. I would have just started off with, I believe, a positive 6 on top and a positive 3 on bottom, which would still give me a positive 2. So don't worry too much about which one you pick. Just make sure that your 1s are together and your 2s are together. Now, I have a slope of 2. In order for me to use the point slope formula, I need a slope and I need 1 point. Don't get distracted by the fact that they have given you 2 points. You only need to pick one of them, and it doesn't really matter which one you pick. I'm going to go ahead and pick the 1 and the 3 because these are both positives and I prefer to leave out as many negatives as I can. Again, if you had picked -2, -3, you will end up getting the same answer. And in fact, I recommend that you try that on your own if you have the time. I plug those values in. Remember, I don't want to put a value in for my unknown x and y. I want to leave those blank or leave those as variables. Distribute your 2. Add your 3, and there's your solution. This equation in slope-intercept form would pass through the point 1, 3 and through -2, -3. In fact, you can see that if you want. If I plug in a 1, 2 times 1 is 2, plus 1 gives me the 3. If I plug in a -2, 2 times -2 is -4, plus 1 gives me -3. Again, if you have the time, I would recommend that you try this again on your own, but when you do it, plug in your x as -2, plug in your y as -3, and again, if you plug those into your equation, you should get the exact same result. Tell you what, take just a second, pause the video, try this one on your own. We're writing an equation for a line that passes through 9, 2, and 3, 5. I am going to do this one just a little bit faster because you should have done this on your own. We need to find our slope, so I plug in my values. 5 minus 2, 3 minus 9 gives me a slope of 3 over -6, which is a slope of -1/2. I have a slope of -1/2. I can pick either of these 2 points to plug in. It does not matter which one you pick, but you cannot use both. Also, keep in mind that if you use the 3, you have to use the 5. If you choose to use the 9, you have to use the 2, because what we're looking for is an example of a coordinate. We can choose either example we want, but once you pick one, you've got to be consistent. I always rewrite my formula, plug in the numbers we were given, use my distributive property on the -1/2, and then I'm going to use the property of equality to add 5 to both sides, and you get y equals -1/2x plus, remember this is 1.5 plus 5 plus 6.5. There you go. Again, if you wanted to check these values, you could plug them in and check those on your own. Don't be thrown off if you are given these in function notation instead of giving them as coordinates. Keep in mind that this says if you put in an 8, you get out a -1. So this is the coordinate 8, -1. And if you plug in a 6, you get out a 0. So that's the coordinate 6, 0. We like to write things different ways, so just make sure you're aware of those different ways. Once you have that information, you're going to do the same thing. So I'd recommend you pause the video and try it on your own. I'm going to keep going, again, moving just a little bit faster because you've already done this on your own. Once again, I got a slope of -1/2. I'm going to pick either point. I picked the 6, 0. I like the fact that this is a positive, that there's no negative signs. I also like this 0 right here. That's going to save me a little bit of work down the road. Rewrite the original formula. Substitute in the values you're given. Make sure you use your distributive property to give this -1/2 to both. And then because I have a -0, I don't need to use the property of equality. The identity property says that adding 0 doesn't do anything, and a -0 is the same as a 0. There you go. Here's one last example. The student council plans to sell plastic megaphones for students to use at the upcoming football game. The table shows the cost for various numbers of megaphones. Can this be modeled with a linear equation? If so, write a linear model in slope-intercept form that represents the cost y of buying x megaphones. Give the cost of 200 megaphones. So there's a lot of things we're asked to do in this problem. Notice we're asked, can this be modeled as a linear equation? And we're told that the cost is y. I'm going to write that down. The cost is y, and the number of megaphones is x. Go ahead and write that in so it's less confusing. The only way we can tell if this can be modeled as a linear equation is if it has a constant rate of change. Remember, linear equations are always going to grow at a constant rate of speed. So I'm going to look at these two patterns and see if we have a constant rate of change. Notice the cost goes from $17 to $22. That's a growth of 5. Then a growth of 5 more, 5 more, and 5 more. Our cost seems to be growing at a constant rate. Let's look at the number of megaphones. We went from 4 to 6. That's a growth of 2 megaphones. 2, 2, and 2. We seem to be growing by $5 every time we buy 2 new megaphones. In other words, if my slope is the change in y versus the change in x, or the rise compared to the run, I am growing by $5, that's my change in y, every time I increase by 2 megaphones, which is a change of $2.50 for each megaphone. Notice that I didn't go through here and calculate the 5 and the 2. You could pick any set of values here and you could compute the slope that way, but since we already did it with the 5s and the 2s, I didn't bother. Now that we know it has a constant rate of change, we could say, yes, this is linear. So I would write the word yes someplace. Yes, it is a linear equation, or yes, it can be modeled by a linear equation. If so, we need to create that model. In order to create the model, we need the slope, which you already have. That's the 2.5. And then you need one example or one point. Notice the table gives us 5 different examples. It does not matter which example you pick, any of them will give you the exact same answer. In fact, I would encourage, if you have extra time after we work this one out together, pick a different coordinate or a different example and use that one and see if it works as well, because it should. I think I chose the 4 and the 17. In general, I like to pick positive numbers. I like to pick small numbers. If I can include a 1 or a 0, I certainly am going to do that. You've already done the hardest part of the problem, because now you're just going to take your pattern, you're going to plug in the values that you said would work, and then we're going to use our distributive property to distribute that 2.5. Notice you get y minus 17 equals 2.5x minus 10, and then you're just going to use the property of equality to put it into slope-intercept form. So then, once we have this pattern, we know that there seems to be a growth of $2.50 per megaphone, and it looks like if we were to buy 0 megaphones, we would still have to pay $7. Now, most people would say, well, how can they charge us $7 for 0 megaphones? Remember, this is a starting point or starting value. So chances are, whatever company we're ordering these through has a minimum charge of $7. Maybe this is a processing fee, maybe it's a shipping fee, but whatever it is, they're going to charge us this one time and then $2.50 for every megaphone. Knowing this, it says give the cost of 200 megaphones. Remember, the number of megaphones is our x, so I'm just going to take my initial pattern, plug the 200 in so I can solve for this specific cost, and it comes out as 2.5 times 200 is 500, plus 7 is $507. Again, the idea here is to give you an example of when the point-slope formula becomes very helpful for us. Notice we were not given a y-intercept, but we were given lots of points. We use those to find the slope, take the slope in any of those points, and we can find our equation. That's all I have for today. Hopefully this has been useful to you. Thank you so much for taking the time to tune in. If this has been helpful, make sure you give us a big thumbs up so that we can see that you're watching. Also, Also, make sure you ring that bell to turn on your notifications so that you can receive all the new material coming up from us here at Nunley Math. As always, I do wish you all the very best. Take care of yourselves. Bye.